Hello everyone, welcome to another week in Intro to Analysis. This week is week 13, and we are going to continue to talk about some consequences of the theorems that we looked at last time pertaining to derivatives. We're going to talk about local maxes and mins. We're going to talk about and prove the mean value theorem. And then we're going to prove L'Hopital's rule for the 0 over 0 case. So without further ado, let's begin. So last time we left off in this section in Cummings' textbook talking about local maxes and mins. And typically when you teach a Calc 1 course, or if you take a Calc 1 course, your professor or your teacher will tell you that a local maximum is going to be a hump in your graph where all of the points are lower than or equal to that hump, but they have to be near the hump, right? So something like this. And likewise with a local min, your teacher probably tells you, okay, it's going to be the lowest point on that curve relative to some points nearby it. And so we're going to make that definition precise here, reformulating it in terms of deltas. Okay, so what do we say? We say, okay, we have a function from a to the reals. We say that the function has a local max at some c in our domain if there exists a positive delta, so that for every x in that neighborhood centered at c, that delta neighborhood centered at c, this implies that f of x is going to be less than or equal to f of c. And so, what this is saying is that there exists a neighborhood, not for all neighborhoods. And why is that the case? Because if we let's consider this neighborhood centered at C, a big delta neighborhood. Well, then this definition does not hold true. There are f of x values, namely this guy right here, that is strictly greater than f of c. So we want to make our neighborhood small enough so that this definition holds true. And so the idea here is we can find a small enough neighborhood. Here's my c minus delta, and here is my c plus delta, so that for any x in this neighborhood, f of x is going to be less than or equal to f of c, right? We can see that all of these little blue points are shorter than this guy, which is f of c. And we have a similar definition for local min. So I'm calling this guy c prime, and we say that f has a local min at c prime in our domain if there exists some delta prime neighborhood, so that any x in that delta prime neighborhood centered at c prime implies that f of x is bigger than or equal to f of c prime. So we have a similar situation here. We have to make sure that our delta prime neighborhood is small enough so that any of these x values in this neighborhood, when you apply the function to them, those guys are going to be sitting bigger than or equal to f of c prime, which we do see is true here. All of these, maybe I'll do them in blue. Maybe I'll do them in red. All of these guys, these f of x values, are higher than or equal to f of c prime. Okay, so that's the analysis way of saying local max and local min. So let's prove this proposition, 7.1. So suppose I is an open interval, and suppose we have a function from that interval to the reals. Suppose further that it's differentiable at c in this interval. So our hypothesis is that if f has a local max or min at c, then f prime of c has to be 0. Okay, so we have some things to work with here. Now, I am going to do the case where we have a local max at c, but the proof for a local min is completely symmetric to the proof for a local max. So we won't worry about doing that. So let's go ahead and do the proof. Well, what are we given? We're given that f is differentiable at c. So we may as well write what that means in terms of our limit definition. So since f is differentiable at c, by definition, this means that the limit as x goes to c of f of x minus f of c over x minus c exists. And this is equal to f prime of c. And what we are trying to show is that limit is equal to 0. So we want to show that this limit indeed equals 0. Okay, so I'm just going to put a box around this for now. What else do I have? I have that f has a local maximum at c. So let's write that down. Since f has a local maximum at c, well, this implies, again, by our definition that we just looked at, definition 7.2, this means that there exists a delta so that whenever x minus c absolute value is less than delta, this implies that f of x is less than or equal to f of c. Okay, so this is just using the definition of local max from definition 7.2. Okay, so we're trying to march along to something that looks like this. So what could I do to make it look like that? Well, I could definitely subtract f of c from both sides, and that's going to give me f of x minus f of c is going to be less than or equal to 0. Okay, now if I want to divide by x minus c, I have to be careful because the difference between x and c could be negative and it could switch the sign around. So we have two choices to work with, right? So if x minus c is positive, when we divide by x minus c, no signs get flipped. So f of x minus f of c divided by x minus c is going to be less than or equal to 0. No harm, no foul, right? And if x minus c is negative, the sign will flip. Well, this is going to imply that when we divide by x minus c on both sides, that's going to flip the inequality. Okay? So we really have two choices for what this can be, depending on whether or not x is bigger than c or x is smaller than c. Okay, so let's write that out. So we have f of x minus f of c over x minus c is equal to, or maybe we should write it like this. Let's say that this is less than or equal to 0 if x is larger than c, and it's bigger than or equal to 0 if x is smaller than c. Okay, so the idea here is we're trying to take the limit of this thing, right, as x approaches c. But we have two cases to worry about, and that is when x is bigger than c or x is smaller than c. Okay, so we want to look in our neighborhood to the right and to the left of c, and what we want to do is we want to produce some sequences converging to c, which we can because we're working with an open interval. So we can produce sequences on the left side and the right side of c converging to C and show that that the sequential definition of a limit holds here, and that f prime of C is going to give us 0. Okay, so that's the idea of where we're headed with this. Okay, so now we already said that the limit exists, right? We know that this limit right here exists. And so by the sequential criteria for limits, if I have a sequence converging to C, then when I plug in my sequence in for x, that thing is going to converge to f prime of C. Okay, so let's write that down. So suppose we have a sub n. So we have the sequence in our neighborhood, and our neighborhood, let's not forget what our neighborhood is. So this is our neighborhood centered at C and a radius of delta. So this sequence is going to be in C minus delta, C plus delta. Okay, so it looks like this. Let's draw it out. Here's C in the middle. Here's C minus delta. Here's C plus delta. And here's my sequence A sub n. That is to the left of C. So x is less than C. That's the case we're doing here. Right? So I have my A sub n converging to C. And by the definition, of sequential criteria for limits, we have the following. Okay, we know by assumption that the limit as x goes to C, f of x minus f of C does indeed equal the derivative at C. And since we have a sequence converging to C, by the sequential criteria for limits, that says that if I plug in the sequence value in here, that thing is going to converge to f prime of C, right? So we have, so I'm just plugging in the A sub n minus f of C over, I guess it's not going to let me go down much further, so we might have to backtrack, but that's okay. So this is converging to f prime of C. Okay, and this is just by sequential criteria for limits. Okay. All right. So what do we have here? So we have that for each n, f of a sub n minus f of c over a sub n minus c is going to be what? Well, if we scroll back up to this guy, all right, so we had this guy right here, and we're just replacing x with a sub n, right? And so where was a sub n? A sub n was to the left of c. It was less than c. So this piece is true. So it's going to be bigger than or equal to 0. So let's write that down. So for each n, it follows that f of a sub n minus f of c over a sub n minus c is going to be bigger than or equal to 0, and that's just from this fact right here. Okay, so if we take the limit of something that's always bigger than or equal to 0, that's going to be bigger than or equal to 0. So applying the limit, where am I going to write this? Maybe I'll just write it off here and then I'll erase some stuff. So therefore the limit as n goes to infinity of f of a sub n minus f of c sub n minus c. Well, we know what that limit is. It's f prime of c, just by the sequential criteria for limits. So that's what it means for this to go to f prime of c. We mean that we're letting n go to infinity. And so this is going to be equal to f prime of c. And we just said that this was bigger than or equal to 0, so its limit is certainly bigger than or equal to 0. So we have that f prime of c is bigger than or equal to 0. And remember, what we're trying to show is that it actually equals 0. So the next piece of this proof is that we're going to find a sequence on the other side of c, all right, b sub n. And we're going to show that this guy, when you complete the steps like we did for a sub n, we're going to get f prime of c is less than or equal to 0. And so greater than or equal to 0 and less than or equal to 0 implies that f prime of c must equal to 0. Okay, so let's go ahead and write that down. So similarly, and again, we can find these sequences because we're working with an open interval. We can always find a sequence converging to anything in our open interval. So we found a sub n. So consider b sub n converging to c. Okay, so that's this guy. Then, for each n, since b sub n is on the right of c, that's going to be this guy, right? So that tells us that for each n, f of b sub n minus f of c over b sub n minus c, this time is going to be less than or equal to 0. Okay, and that's by this guy up here. All right, and so, following the same process that we did before, taking the limit, what we get is that the limit of this guy we know is going to be f prime of c. And so that implies that f prime of c, since this is less than or equal to 0 for every n, when I take the limit, that limit better be less than or equal to 0 as well. So f prime of c is less than or equal to 0. And since we have this guy and this guy, it must be that f prime of c is actually equal to 0. And we are done with that proof. Okay? So I kind of wrote this slide upside down, but let's recall the intermediate value theorem. So if we have a continuous function f on a closed bounded interval, and you have alpha as any number between f of a and f of b, then there's some c in the open interval from a to b for which f of c is equal to alpha. And we kind of had this picture in our head, right? So here was our function f. So let's say this is a, and let's say this is b, and it's continuous. Okay, so this is f of b and f of a. This was f of a and f of b. And so what the intermediate value theorem told us was that if we have alpha in between f of a and f of b, that there's some c in our open interval from a to b for which f of c is equal to alpha. And we can see this on our picture here, that this c in particular is the one that will satisfy this. So the derivative version of this is pretty similar, but we don't require that our derivative function is continuous. So here's the theorem. It's called Darboux's theorem. And I'm not going to give a proof of it, but we are going to use it in a problem. So this is what it says. It says if you have a function from A to B that's differentiable, i.e. continuous. And if you have alpha between f prime of A and f prime of B, so you can think of alpha as a slope. Okay, so think of a slope between this slope and this slope. Then there exists some value c in the open interval from A to B, so that the slope is equal to alpha. F prime of c is equal to alpha. And that kind of makes sense. But the key distinction here is that your derivative does not have to be continuous for this to hold true. Okay, so that's the big distinction here. And, so like if you have, let's say that f prime of A, let's say that the slope of the tangent line to A is equal to 2, and then the slope of the tangent line to B equals 3. Well, let's say that alpha is equal to 2.5, right? So what this is telling us is that there is some c value in our interval where f prime of c is equal to alpha. So the slope of the tangent line of f at c is going to equal 2.5. And maybe we can draw it. So here's A, here's B, and let's say it goes like this, and maybe it's slightly steeper right there. I don't know if I drew this to scale, probably not, but let's just say that this guy is f prime of A. So the slope of this tangent line is 2. And then f prime of B is a bit steeper. Let's say that f prime of B is 3. And so Darboux's theorem guarantees that there's some c in between these guys that has a slope of 2.5. So this is m equals 2.5, and let's say that this is our c value. Okay, so that's the idea here. And the next theorem we want to look at is Rolle's theorem. Probably learned this in Calc 1, but we're going to go ahead and prove it with what we have derived so far in this course. And so here's what it says. It says if you have a function on a compact interval, a to b into r, let it be continuous and differentiable on the open interval from A to B. Then, if f of A equals f of B, there is some c in the open interval where f prime of c equals 0. And I think this makes sense when you look at the picture. So if you have f of A and f of B are equal to each other, okay, if you have something like this, well, I guess the idea is like, okay, so I have a positive slope at A, I have a negative slope at B, and so the idea is like, okay, well, I have to have some point where the slope is 0, right? And so that's Rolle's theorem. So let's go ahead and prove it. All right, so the idea is we're going to use the extreme value theorem here. And if you recall, the extreme value theorem says that on a compact interval, f achieves its maximum and its minimum. Okay, so since our interval A to B is compact, by the extreme value theorem, there's some C1 and C2 in our interval, so that f of C1 is equal to the max, and f of C2 is equal to the min. So that's just what it means to achieve its max and min values on the compact interval. Okay, so let's go ahead and draw a picture. Maybe while I use, let's go ahead and draw another separate picture off to the side. So here we have A, here we have B, okay. And so here's our little function here. Okay, so there's our function f. Okay, so if we have, so C1 is the max and C2 is the min, so it looks like from how I drew my picture that this guy is C1, the max, and that this guy right here is the min. Okay, and what are we trying to show? We're trying to show that there exists some point in the open interval from A to B where f prime of C equals 0. And we know that by proposition 7.1, this guy right here is a min, hence a local min, and this guy right here is a max, hence a local max. And so we know that f prime of C1 and f prime of C2 will both be 0 in this case, if C is in between A and B. So if C1, C2 are both, or if one of them is in the open interval from A to B, then the theorem is shown by proposition 7.1. And so let's assume that that they're not in the open interval, but let's actually assume that they are endpoints. Okay, so that's the other case that we're working with. So the first case is if one of them is in between A and B without equaling A or B, then the theorem is shown because of proposition 7.1. We know that the derivative at local maxes and mins are going to be 0. But let's look at the case where they're endpoints. So without loss of generality, so I'm just choosing C1 to be A in an arbitrary way. So suppose that the C1 and C2 are actually the endpoints. Okay, and so what does that mean? Well, this is going to mean that f of x is bigger than or equal to f of b, which is less than or equal to f of a. And this is just by the definition of max and min. Okay, we said C1 was A, and f of C1 is the max, and so that means that f of A is going to be bigger than or equal to any other guy on AB, and since f of B is f of C2, this is going to be the min, so yeah, f of B is less than or equal to f of x. Okay, so we know that that is true. Okay. Since by assumption, so what was our assumption? Our assumption was that f of A is equal to f of B. Okay. We have f of A equals f of B. This is going to imply, by this inequality here, that f of x is forced to be f of A and f of B for all x in our interval. And so what does that mean? If the function is not changing for all x in a, b, That just means it looks something like this, right? Function is not getting any steep or anything like that. So that means that our function is constant. So is constant. And we know that the derivative of constant functions are 0. So that means that f prime of x is equal to 0, which implies that there is a c in our interval from a to b, so that f prime of c is equal to 0. Okay, in fact, every x in this open interval. Okay, so that is the proof of Rolle's theorem. And we're going to use Rolle's theorem in our next theorem, which is the mean value theorem. Okay, so this one is pretty important, and I'm sure that if you taught calculus, you've definitely covered this. So let's go ahead and prove it. So what does the mean value theorem say? Well, I'm going to first just disclose that sometimes I'll abbreviate it MVT because I'm lazy. So what does it say? It says that if we have a function on the compact interval from a to b into the reals and it's continuous and differentiable on the open interval from a to b, then there's some c in that open interval where the derivative of c is just equal to the slope of the secant line that connects a and b. Okay, so we have a picture right here. In green, I have my function f. I have I have a comma f of a labeled as a point, and b comma f of b labeled as a point, and I'm forming the secant line that's red in between those points. Now the slope of that secant line, rise over run, or with the formula, is just the difference of f of b and f of a over b minus a. And our claim is that this is actually going to be f prime of c for some c that lives in, the open interval from a to b. All right, so the first thing we're going to do is we're going to find the equation of the secant line, and then we're going to consider the difference between the function f of x and the secant line, which I've labeled in red. And then we're going to use Rolle's theorem, okay, to get what we want, which is that f prime of c is equal to the slope of that secant line. Okay, so let's do it. So find the equation of red secant line. Let's go ahead and do that first. All right, and so, I don't really teach point slope to my algebra students, but if you want to use point slope here, you certainly can. But the idea here is that the equation of this line is going to be y equals m. What's the slope of the line? Well, that's just fb minus fa over b minus a times x plus our y-intercept, which we're not sure of yet. And we can solve for that y-intercept by just plugging in a point for x and y. And how about the point a comma f of a? So this is going to give me f of a equals this. Again, you could just use point slope here, not a big deal. Okay, and when you isolate b tilde, or our y-intercept, this is going to give us f of a minus a times f of b minus f of a all over b minus a. Plugging this into the original equation, we have y equals f of b minus f of a over b minus a times x plus f of a minus a times f of b minus f of a all over b minus a. Okay, and I can go ahead and do some factoring here. I can factor out, I can factor out an x minus a from this guy that has that in common. So if I pull that out, I'm left with okay, so this is the equation of my secant line. All right. So now what we're going to do is we're going to consider d of x as the difference between our function, so f of x, and the secant line. And that's going to be, like, if you look visually, this distance right here, this distance right here, this distance right here are going to be outputs of that function. So consider d of x, which is the difference between f of x and the secant line, which we just found the equation of. Okay, so what does that become? Well, that's just going to be d of x is equal to f of x minus that secant line Okay, and so what can we note here? Well, by hypothesis, this guy was differentiable on AB, and we know that linear functions, lines, are differentiable everywhere. And so the difference between two differentiable functions is also going to be differentiable on AB. Okay, so dx is a difference of functions differentiable on AB. Thus, dx is differentiable on AB. Okay? All right. Also, notice that d of a, if I plug in a into this function, I get f of a minus blah, 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 b minus a times a minus a, blah, blah, plus fa, blah, blah, blah. Okay, so this goes to 0, and then we have f of a minus f of a goes to 0. And so you do the same thing when you plug in b in here. So this is going to be d of b. And so the idea here, the little slick trick, is that we can now apply Rolle's theorem. Because we have that d of x is differentiable on a, b. We have that d of a equals d of b. So by Rolle's theorem, there's some c in the open interval so that d prime of c equals 0. Okay, so let's write that out. So by Rolle's theorem, there exists c in that open interval such that d prime of c is equal to 0. Okay? Now, d of x, if we go back up to d of x and we take the derivative of this function with respect to x, well, I take the derivative of the pieces, right? So d prime of x is going to be f prime of x. This guy's constant, okay? And so when I take the derivative of x minus a with respect to x, that's just going to give me, well, I mean, you can think of it as like this whole thing. Taking the derivative of that whole thing, you're going to get f of b minus f of a over b minus a, because this is just a constant times x. And then minus a times a constant. I mean, that's a constant too, so that disappears with the derivative. And then this is a constant, so that disappears. And so when you take d prime of x, you're just left with f prime of x minus f of b minus f of a over b minus a. So let's write that down here. So that equals that minus f of a over b minus a. Okay, and so we know that d prime of c equals 0. So if I plug in c for my x values, I get d prime of c equals f prime of c minus f of b minus f of a over b minus a, but hey, this equals 0. Okay, so then if I add this to both sides, I get exactly what I wanted. So f prime of c equals f of b minus f of a all over b minus a, and there we are, we have just proved the mean value theorem. Okay, so now that we have some new theorems in our toolbox, let's go ahead and put them to work. So let's look at this example. So we have that h is a differentiable function. Let h be differentiable and let it be defined on 0, 3, compact interval. And assume that h of 0 equals 1, h of 1 equals 2, and h of 3 equals 2. Okay, so we want to prove first that there exists some d in the closed interval from 0 to 3 so that h of d equals d. Well, we know that h of 0 is not equal to 0. We also know that h of 3 is not equal to 3. So this becomes finding something in the open interval from 0 to 3 that has this property. So I think I assigned you a problem kind of similar to this, but let's just go through it. I think this was maybe last week with our intermediate value stuff. And so we claim that there is some d in the open interval from 0 to 3 such that h of d equals d. Okay, and so if you remember this trick with the intermediate value theorem, we defined, like we took the difference on both sides by d and we defined a new function, right? So let's go ahead and do that. So we're going to let g of x equal h of x minus x, right? So this is our new function g, and I'm defining it because if I subtract d from both sides, I get that this equation is equivalent to h of d minus d equals 0. So really what I'm trying to do is to show that this guy has a root, that this equals 0 somewhere for some x. And I can do that by the intermediate value property, or the intermediate value theorem. Okay, so here's the idea. We know that g of x is the difference of two functions which are differentiable on 0, 3, hence continuous on 0, 3. And since g is continuous on 0, 3, we can apply the intermediate value property. Okay, so we can apply IVT. We have the following. We have that g of 0, well, g is just h minus x, so that's going to be h of 0 minus 0, and h of 0 is 1. So 1 minus 0 is 1. We have that g of 3 is h of 3 minus 3, and that is going to be 2 minus 3, which is negative 1. Okay, and so the intermediate value theorem says, okay, if we have this continuous function between 0 and 3, let me draw it a little bit more accurate. So we have this continuous function, and we had that g of 0 was 1, and that g of 3 was negative 1. Okay, so the intermediate value property says that there has to be some c in between 0 and 3 for which g of c is equal to 0. Okay? Or d in this case. So thus, by IVT, there's some d. I should have called it d there. D in 0, 3, for which g of d equals 0. Okay? And g of d being equal to 0 implies that h of d equals d. Thus, h of d equals d. And so we're done there. Okay, so that was just using some things that we learned last week. Okay, so here's the next portion where we're going to use some new stuff. We're going to argue that there is a c between 0 and 3 for which h prime of c is equal to 1 over 3. Okay, so we see derivatives, and so that gives you a clue, like we're going to use one of these new derivative theorems, Darboux or mean value or Rolle. Let's look at the mean value theorem. What does that say? Well, the mean value theorem says that if h is differentiable and continuous on an interval, then you have f prime of c equals f of b minus f of a all over b minus a. Okay, so let's write that out. So since h is differentiable on 0, 3, it is continuous on 0, 3. So by the mean value theorem, there's some c in this open interval from 0 to 3. So that, okay, remember I'm using this as my a and this is my b in my mean value theorem. So this is going to give us h prime of c is going to equal h of 3 minus h of 0 over 3 minus 0. And so I know what h of 3 and h of 0 is from my assumption. So that's just going to be 2 minus 1 over 3. And that equals 1 over 3. Okay? So there, by the mean value theorem, there is such a c in that open interval so that h prime of c equals 1 over 3. And we're done there. Okay, so now we want to argue that there's some e in 0, 3 such that h prime of e equals 1 over 4. Okay, so notice that what we're told here is that h of 1 equals 2 and h of 3 equals 2. And we know that h is differentiable on 0, 3. So we can apply the mean value theorem here. Oh, sorry, h of 1 equals 2 and h of 3 equals 2. Sorry about that. So h of 3 equals 2. And so by the mean value theorem, there exists some d in 1, 3. So that f prime, or h prime rather, h prime of d is going to be equal to the slope of the secant line connecting our endpoints. Okay, so here we have, so our a is 1 and our b is 3. And so we have h of 3 minus h of 1 over 3 minus 1. And so that's just going to give us 0 over 2, which is 0. Okay, so there's some d in our interval for which h prime of d is equal to 0. We also know from the previous part B, that there is some c in our interval for which h prime of c is equal to 1 over 3. And 1 over 4 is between 0 and 1 over 3. So we can apply Darboix's theorem here. Okay, so if we have a slope in between, then there's some e such that when you take the derivative of h and plug in e, you get your 1/4 value. Okay, so by Darboix, since there exists c for which h prime of c is equal to 1/3, and there exists d in our interval for which h prime of d equals 0, then it follows that there has to be an e in our interval for which h prime of e is equal to 1/4, and that's because a fourth lives between 0 and 1/3. So this follows from Darboix's theorem. All right, so here is a corollary to the mean value theorem. So if we have an interval I and a function from I to the reals, let this function be differentiable. If f is monotone increasing if and only if f prime of x is bigger than 0 for all x. And in a similar way, it's monotone decreasing if and only if your derivative is less than or equal to 0 for all x in your interval. And this should make sense, right? Because if I have maybe a function like this on a domain parabola, we can see that our derivatives are changing, right? So our slope is negative, 0, and then it goes back to being positive again. So it's not monotone increasing or decreasing. It's decreasing on this interval, and it's increasing on this interval. And so the derivatives are not monotone, is kind of what this is saying. But if I have a function that is monotone increasing, like something like this on an interval, well, the slopes are always going to be positive as well. And that's what this is telling us. So let's go ahead and prove this claim. All right, so we're only going to prove the first one because, again, the second piece has a symmetric argument. Okay, so what are we going to suppose? We're supposing that f is differentiable on our interval and that it's monotone increasing. All right, so we'll do the forward direction first. Okay, this is an if and only if. So we're going to assume first that f is monotone increasing and show that this holds, that f prime of x is bigger than or equal to 0. All right, let's do it. So suppose f is monotone increasing. Okay, then for all x1, x2 in our interval, when x1 is less than x2, what does it mean to be monotone increasing? Well, it means the function is growing, right? So here's x1, here's x2. That means that f of x2 is bigger than or equal to f of x1. Okay, and what does this imply? So then we have, if we subtract f of x2 from both sides of the inequality, we get f of x1 minus f of x2 is less than or equal to 0. And from this piece, we have x1 minus x2 is less than 0. So this implies that if I divide this inequality by x1 minus x2, it's going to flip the sign, right? Because this guy's negative. So let's put that here. Minus f of x2. I'm going to divide by this guy, and it's going to flip the sign since x1 minus x2 is negative. So this is going to flip to greater than or equal to. And this is whenever x1 is less than x2. Okay? So we know that this thing is differentiable on our interval. And so if we have that it's differentiable at c in our interval, we have that f prime of c is going to equal the limit as x goes to c of f of x minus f of c over x minus c. Okay, so if c is less than x, then this is going to hold, right? Then we have this inequality, and so taking the limits is not going to change the direction of the inequality. And so, yeah, if x is less than, this should be flipped. Sorry, this should be x less than c. Okay, so if x1 is x, then x2 we can think of as c, and the result holds. This is going to be bigger than or equal to 0, so that works. So this is if x is less than c. So that's what we were trying to show. We're trying to show that f prime of x is bigger than or equal to 0 for all x in the interval, and so we're looking at a specific x equals c. Okay, so that's the case when x is less than c. Okay, if x is bigger than c, then we have f of c. Again, we're using this piece right here. Okay, so we have that x1 is less than x2. So here we're using c in replacement of my x1, and we're using x in replacement of my x2. Okay, so this is f of x minus, or f of c minus f of x over c minus x is going to be bigger than or equal to 0. So then if you do some trickery, just factor out a negative sign and do your thing. This is going to give us this guy over this guy. Okay. All right, and then when you multiply by a negative, the sign flips, but then when you multiply by this other negative, it's going to flip again. And so that's going to imply that f of x minus f of c over x minus c is going to be bigger than or equal to 0. And so the limit as x goes to c, which is our derivative, is also going to be bigger than or equal to 0. Okay, so the forward direction is shown. We've shown that that if we have a monotone increasing function, our derivative at any c or any x in our interval is going to be positive. Okay, bigger than or equal to 0. Okay, so now we need to go in the backward direction. So I'm going to erase some stuff so that I can make room for our backward direction. Okay, so what are we assuming? Okay, so we're going to assume that our derivative is bigger than or equal to 0 for all x in our interval, and we're going to show this implies that f is monotone increasing. Okay, so suppose that our derivative is positive for all x in our interval, and then we'll choose two values in our interval, say x1, x2, and without loss of generality, we'll say that x1 is less than x2. Okay, so we want to show that f is monotone increasing. So we want to show that if this is the case, if x1 is less than x2, this is going to monotone increasing tells us that we should show that f of x1 is less than or equal to f of x2. Okay, so now we can apply our mean value theorem to finish the proof. So by our mean value theorem, there exists some c in this interval from x1 to x2, so that f prime of c is going to be the difference between f of x2 minus f of x1 all over x2 minus x1. And we have that x1 is less than x2, and so that means that x2 minus x1 is bigger than 0. So x1 less than x2 implies that x2 minus x1 is bigger than 0, just rearranging the inequality here. And by assumption, we have that f prime of x is bigger than or equal to 0 for all x in our interval. So in particular, c is in our interval, right? If c is in this smaller set, then it's certainly contained in our bigger interval. So in particular, this means that f prime of c is bigger than or equal to 0. Okay. And so since we have this right here, this means that f of x2 minus f of x1 over x2 minus x1 is bigger than or equal to 0. Now, because x2 minus x1 is bigger than 0, when I multiply both sides by it, I'm not going to flip the inequality. And I'm just going to get f of x2 minus f of x1 is bigger than or equal to 0. And therefore, f of x2 is bigger than or equal to f of x1, and the claim is shown. And you can show the monotone decreasing case in a very similar way. Okay, so this is the Cauchy mean value theorem. Sometimes they call it the generalized mean value theorem. And very similar to the mean value theorem, just a general form. So if we have two functions that are continuous on our closed bounded interval from a, b, and differentiable on the open interval from a, b, then there is such a c such that this holds. Okay, and notice that you can divide both sides by g prime of c, assuming that it's non-zero, and you get this equality right here. So this is the generalized mean value theorem, and I'm not going to prove it, but you guys can investigate this in homework. I think I'm going to assign this for homework. I'm not entirely sure, but we do need this theorem for our next proof. So, without further ado, let's talk about good old L'Hopital's rule. I don't know about you guys, but I used to call this L'Hospital's rule in high school like a dummy, and sometimes I still do, because sometimes it's fun to be silly. So anyway, here's L'Hopital's rule. I'm just going to talk about the 0 over 0 case. the infinity over infinity or negative infinity over negative infinity, etc., the proof is similar, so we're not going to do it just for the sake of time. But anyway, let's talk about what this says. Okay, so if we have an open interval containing a point A and a function from the interval to the reals, another function g from the interval to the reals, differentiable in I, except possibly at A. Okay, so if you go on YouTube, like I did because I was about to teach this, there's a lot of proofs that rely on these functions actually being differentiable at A, that their limit exists, but we're not going to play that game. We're going to prove a more general case where that the derivative might not exist at A, and so our proof has to be a bit more involved than you know, what you might see on YouTube, unfortunately. Okay, so further, suppose that g prime of x is not 0 on our interval. Okay, so we're not going to have a 0 denominator here. That's good. Okay, and so then if we have the limit as x goes to a of f of x being 0 and the limit as x goes to a of g of x being 0, then this follows. So when you take the limit of this guy and you get 0 over 0, as we show our calculus students, you can simply take the derivative of the numerator and the denominator and plug in a. And if it doesn't work, if you get 0 over 0 again, you can use L'Hopital's rule a second time or a third. So we're going to actually prove this, but just so we remember what this is, here's a small example. If you recall, if you plug in 2 into the top and the bottom of this function, we get 2 cubed minus 7, 2 squared plus 10 times 2, all over 2 squared plus 2 minus 6, and we end up getting 0 over 0. So this is our f of x, and this is our g of x. Okay, and so L'Hopital's rule says, hey, just take the derivative of the top and the bottom, and then plug in, and no problem. So f prime of x is going to be 3x squared minus 14x, just taking the derivative, plus 10. And then g prime of x is going to be taking the derivative of the bottom portion, which is just going to give us 2x plus 1. Okay, so then if I plug in 2, I don't get 0 over 0, which is super nice. I actually get negative 6 over 5. Okay, so L'Hopital's rule says that we can evaluate limits like this in this fashion by just taking the derivatives and then plugging in the limit. So let's go ahead and prove this for the 0 over 0 case. All right, so what is our assumption for L'Hopital's rule? Okay, we have that our function is, well, both of our functions, f and g, are differentiable on this interval I, except maybe not at a, okay? So you can tell all the YouTubers that are doing this, wait a minute, what about, why are you assuming differentiability at a? Anyway, I don't know. I mean, does it work out if we, maybe that's something that you guys can investigate further. If we can make this proof simpler and still not assume differentiability at A. Okay, so something to think about. I don't know. If you're bored, you can try to do this. Okay, and so also we're going to assume that this is not equal to 0 and that these two things hold true. That the limit as x goes to a of f of x is 0 and the limit as x goes to a of g of x is also 0. Okay, so I'm going to write this up here. So our assumptions. Okay, so we have the limit as x goes to a of f of x equals 0. Oops. And the limit as x goes to a of g of x is also equal to 0. Okay, and we're also assuming that's our first, and our second is that fg are differentiable, hence continuous, on I, except maybe not at A. And that's what is making this proof so hard. Well, it will be. I mean, it's not like a super hard proof or anything. It's just more involved than what people do because of this. Okay. All right. So, what do we know? Well, because f and g are differentiable on our interval, their derivatives exist, and because we are only concerned with what x is approaching when x is approaching a and not when x is equal to a, we can say that the limit, we can say that since f and g are differentiable in this entire interval, except maybe not at a, but we don't care about what happens at a with limits. This means that the limit as x goes to a of f prime of x over g prime of x is going to exist, right? We're just looking at what happens when x goes to a, not when x equals a. Okay? All right, so if this exists, let's call it L. So suppose this equals L. Then let epsilon be bigger than 0. Our old friend epsilon is back. What does it mean for the limit to exist? Okay, so we're going back to the functional limit definition using epsilons and deltas. What does that mean? That means that then there exists some delta neighborhood, so that when x is in this delta neighborhood, that means that our function is in that epsilon neighborhood. Okay, but I'm not gonna say epsilon, and you'll see why towards the end of the proof. I'm gonna say epsilon over 2, okay? This time we're not doing any weird addition tricks, but I'm going to show you why we need this in just a second. Okay, so this is going to imply that our function, which is f prime of x over g prime of x, gets arbitrarily close to our limit L. Okay, less than epsilon over 2. Okay, and what does this mean if we break down the absolute value piece? Well, by properties of absolute values, this just means that we have f prime of x over g prime of x minus the limit is going to be less than epsilon over 2, greater than negative epsilon over 2. So unfolding this even more, isolating the f prime and g prime, I get that f prime of x over g prime of x is going to be between L minus epsilon over 2 and L plus epsilon over 2. Okay, so far so good. Now what we're going to do is we're going to ensure that I pick points inside my delta neighborhood. And what this continuity definition is going to give us is that when I apply this derivative to those points, those that function value should be in my epsilon over 2 neighborhood. So let's write that out. Okay, so we're going to consider x1, x2 in my neighborhood centered at A. Okay, so this is right here. This is my neighborhood. I'm going to draw a picture, okay, because I want to look at I want to look at two different pieces. I want to look at what happens when x1 is on the left side of A and when x2 is on the right side of A, just like I did in a few slides ago with that proof. So let's go ahead and sketch it out, okay? And you'll see why we need this, like, when the proof unfurls, okay? So, all right, so we have these two guys in our delta neighborhood, and we have that x1 is less than A, which is less than x2. So let's draw a picture, as we always do. Here is our hood, if you will, our delta hood centered at A, and on the outside is A minus delta. On this other side, symmetric, we have A plus delta. And then containing the whole thing is our original interval that we had, I. Okay, so this is our original interval I. So let's go ahead and maybe put him in right here, or her, whatever. And now I'm demanding that x1 be less than A. So say x1 is right here. And I'm saying that x2 is bigger than A. So let's say it's right here. Okay, so far so good with the picture. Now f and g are both differentiable on our interval I. Okay, well x1, this closed interval from x1 to x2 is certainly contained in this open interval. So in particular, our functions are differentiable on x1, x2. All right, so let's write that down. So since f and g are differentiable on I, then in particular, they are both differentiable on this closed interval because it's contained in I. All right, and so now we're going to use what I didn't prove here, which is this Cauchy mean value theorem. Okay, so by the Cauchy mean value theorem, because f and g are differentiable on x1, x2, hence continuous, then there is some value in between x1 and x2 for which this holds. Okay? Just replacing A with x1 and B with x2. So let's go ahead and write that out. Then by Cauchy mean value theorem, there's some C in my x1, x2, which, by the way, is contained in this delta neighborhood. We need that. Is contained in A minus delta, A plus delta, such that, well, what does the Cauchy mean value theorem say? It says that, we'll look at this piece right here. It says that the difference between f of x2 and f of x1 over g of x2 minus g of x1 is going to equal f prime of c over g prime of c. All right, so f prime of c over g prime of c equals f of x2 minus f of x1 all over g of x2 minus g of x1. But wait a second, c is in here, right? And if c is in here somewhere, then it means that it's in my delta neighborhood. And what does that mean? Well, that means I can simply replace c in here, and that's going to be in my f prime. It's going to be in this epsilon over 2 neighborhood, basically. So that's the idea here. I'm just using that limit definition that we have up there. Okay, so we have the following. We have that f prime of c over g prime of c is going to be in this epsilon over 2 neighborhood, centered at f of f prime of c over g prime of c. Am I saying that right? Sorry, let's... Sometimes these definitions get crazy and I get lost. But let's make sure we're on the right track. Okay, I think we said everything correctly. Yeah, okay, so whenever x is in this neighborhood, that means that f prime of x over g prime of x is going to be in this neighborhood here. So just applying c here, we get that result. So yeah, we're good. All right, cool. So now we have this, but hey, this equals this. So let's write it out. And you'll see where I'm going with this. I looked at the proof that was in the book, and so that's what we're doing. So if you have an easier proof, you know, maybe this is like a bonus points. Okay, I want an easier proof, but you can't assume that f and g are differentiable at a. Okay, so that's the mission. And you'll get a bunch of bonus points. And if I forget about this, just tell me. Look at the YouTube video. Okay. Oh, I literally just wrote the same thing. So here we go. Let's write what we want to write. F of x2 minus f of x1 over g of x2 minus g of x1 is less than L plus E over 2. Okay, and here's why we use the epsilon over 2. Okay, ready? Drum roll, please. Okay, so now, what does this look like? It should look very familiar, like a derivative, right? So the idea here is that we're going to take the limit as x2 goes to a, okay, so that we can unravel this a bit and prove that the limit as x goes to a of f over g equals the limit as x goes to a of f prime over g prime. Okay? So, yeah, we're trying to, we're not trying to look at the derivative, but we're trying to get this in terms of f over g. And I know from my hypothesis that I know that this holds true, that, you know, who cares if I'm saying it's x1, x2? It's still a variable. As x2 goes to a, f of x2 should go to 0, and same thing for g. Okay, I don't care that I'm saying that the variable is x2 and not x1. Doesn't matter. Okay, so here's the crucial piece. Remember, when you take the limit of something and that thing is less than something, well, remember, when you take the limit, that could change to equality, right? So we have this weird thing, this weird function, and it's less than L plus epsilon over 2. So here's L plus epsilon over 2. And so when I take the limit of this thing, it's possible that even though we're not equaling this in the functional sense, it's possible that the limit could actually equal that. Okay? So that's the idea here. So taking the limit as x2 goes to a, well, if I take the limit as x2 goes to a of these pieces, it's not doing anything because we don't have an x2 involved. And similarly, if I take the limit as x2 goes to a of this piece and this piece, we still can't do anything with it because it's not dependent on x2. We just have to leave it there. So here we have, when we take the limit, this less than and greater than sign, remember, we could achieve these values as the limiting values. So we want to incorporate a less than or equal to instead of just a strictly less than, strictly equal to. Okay, so by hypothesis, when I take the limit of this guy, taking the limit as x goes to, or as x2 goes to a of f of x2, well, by hypothesis, this is just going to be 0, right? This was x right here, but it doesn't matter. It's just another variable. This is going to be 0. And similarly for g of x2, the limit as x2 goes to a of g of x2 is going to be 0, and this is just by our hypothesis 1. So what we have is, like, once we did our replacing with the zeros, right? We had f of x2 went to 0 and g of x2 went to 0. Well, now we have this guy. And so by absolute values, this is going to tell us that f of x1 over g of x1 minus L, absolute value, is going to be less than epsilon over 2, which is less than epsilon. And so, you know, the key idea was that we were looking at a value over here, but we can also look at a value in this neighborhood and get the same kind of argument with x2. So similarly, we can apply the same argument to show that f of x2 over g of x2 minus the limit, absolute value, is going to be less than epsilon. So what does that say? Well, we took care of stuff over here. We took care of stuff over here in this delta neighborhood. So in fact, for any x in this delta neighborhood, this works, right? And so we have the limit statement that we want here. Okay, so thus for any, so we looked at stuff on the left and stuff on the right, but since both of these arguments produce the same thing on the left and the right side, for any x in this neighborhood, we have absolute value of f over g minus the limit is going to be less than epsilon, and hence the limit as x goes to a of f over g equals L. And by assumption, this was equal to the limit as x goes to a of f prime of x over g prime of x. And so L'Hopital's rule is shown. Like I said, if you have an easier proof that that doesn't rely on being differentiable at a, let me know. Thanks for watching, you guys, and I'll see you guys next time.